Here's the prelab8, the ideal gas law. And ideal gas law will work well at this temperature and pressure. Gases tend to act ideally at low pressure and high temperature. High pressure, something like the surface of Venus, like 100 atmospheres, or low temperature, like close to liquid nitrogen. Gases don't act very ideally, and they have attraction for each other. And we are going to use hydrogen peroxide. We're going to look at the percentage hydrogen peroxide. It's normally 3%, but it's not going to be 3%. You can stabilize a little bit by putting some acid in there, but it's typically not. And hydrogen peroxide, don't let it mix with metals. Don't store hydrogen peroxide in metal containers. You can create explosives. Not like explosives that use to blow up a building, just really shock-sensitive explosives that might blow up in your hand, for instance, if you move the bowl. So it's not a very good thing to do to store hydrogen peroxide in metal containers. And it forms oxygen gas, and if you put it on a wound, it'll get kind of fizzy with your blood. Because your blood has some enzymes in it, it will release the oxygen. And you can use it to dissolve scabs. So only use hydrogen peroxide initially to clean out a wound. If you continue to use it, your cut pretty much is just not going to heal. But it's okay for like initially to use it. It's also used in your hair to color your hair. It's also, for instance, OxyClean has got sodium carbonate infused with hydrogen peroxide. Uses it for cleaning things. And here's the ideal gas law. PV equals nRT. Pressure times volume equals the number of moles times the gas constant times the temperature. Pressure and volume are they're inversely proportional, meaning when one goes up, the other one goes down, and vice versa. Pressure and volume is directly proportional to the number of moles and the temperature, meaning if you up the number of moles, the pressure goes up. Also, the volume goes up. If you up the temperature, the pressure goes up, as does the volume. That's directly proportional. Inversely proportional is when one goes up, the other one goes down. That's pressure and volume are inversely proportional to each other. And here's a reaction. 2 moles of hydrogen peroxide are going to produce 2 moles of oxygen and 1 mole of oxygen. Solving for n, this is going to come in later, the number of moles is pressure times volume divided by the gas constant times the temperature. And the amount of how many moles of O2 you can get using this equation here. The amount of hydrogen peroxide used times the density. This is the volume. This should be volume H2O2 used. Density, molecular mass, mole conversion. This mole conversion comes from here. The 1 mole O2, 2 moles. It's because 1 mole here to 2 moles there. And we're going to use this and then get the actual moles divided by theoretical moles and see if any decomposition has occurred. And you will see decomposition. I doubt you'll be like my football coach. My football coach always told me to give 110%. You're not going to give 110%. Heck, you're not even going to give 100% in this lab. You're going to give less than 100% by various means. And what is the yeast? There's a catalyst that promotes it. Ideal gas law, it's up there. So here, how many moles O2, so barometric pressure, so that's the outside pressure, temperature 298. So this is N equals PV over RT. So here's pressure, here's volume, R is given, there's temperature, you can solve for that. 10 milliliters of 100% H2O2, how many moles O2? So let's go back up here. So it's going to be 10 milliliters times 1.02 times this. That will tell you the theoretical. But remember, this is for 100% hydrogen peroxide. We're using 3%. And so we're going to do the ideal gas law. Here's the experimental setup. If you don't have a ring stand, you're just going to have to hold this. And so fill this thing up with water and invert it. You're gonna get a little bit. So start with this, and this is a beaker. Take your beaker. Maybe even if you're doing this at home in your kitchen, it might be even better if you grabbed a medium-sized pot. That'll work as well. And you fill this thing up with water, and it says use distilled water, but I mean, come on, you can use tap water, it's fine. And then you invert it, and then you're gonna get a little bit of bubble. Try to avoid the bubble, but you're gonna get it. And that's your initial volume. And then take your Erlenmeyer flask and the kit. These are typically plastic, and they have a screw top on top. Take your stopper and your tubing and your tube, and then stick it in here. You can hold it by hand if you have to. This can be done that way. And then you put, so with the procedure, you put the solution with the yeast in here, and then stop it as soon as you can, and then it's going to collect gas. It's gonna be kind of slow to start off, and then it'll finally start to fizz. And you know, I mean, play some music or watch your TV, play with your iPhone or something, because it's gonna be like a boring 10 minutes or so where you're holding the thing while it's reacting. I mean, if it makes you feel better, I've spent months of my life watching water boil. That's just the joy of being a chemist. I've spent so much time watching water boil or water heat up or ice melt. That's just, you know, so hopefully you won't be upset about 10 minutes of your life being wasted holding this container. And just think about how much you're doing for science while you're doing it. If you can hold on to this, and the temperature, if you up the temperature, that'll make it go a little faster. If you want to dunk this in warm water, that'll make it, not like boiling water, you'll kill the yeast, but you know, if you put this in warm water, that might speed things up too. I mean, don't put it in ice. You'll be sitting here for 2 hours if you put this in ice. But you know, just warm this up. That'll make things go faster. And then, so that's pretty much the procedure I just went over. And at the end, what you're looking for at the end is this volume of gas. It's the air is initially there. And also, what we didn't talk about was the vapor pressure of water. We're hoping that the vapor pressure of water is contained in that air bubble so that we can get rid of that. That's for a more advanced chemistry class. But we're hoping that it will all fit in there. So we have the water temperature, the barometric pressure. Just look it up, you know, on the internet. You know, find the barometric pressure of wherever you're at, and that will it's going to be typically close to an atmosphere, and sometimes it's in inches of mercury rather than that. So if you get that, let's look at so if you see barometric pressure, so you can find different websites that have, okay, this one's not looking for that. You can find different barometric, here we go, barometric pressure is 30.7, or so 30.07 inches mercury, and you can find conversions. Well, actually, you don't even have to inches mercury. You can just convert inches to see here. You can type in 30.7. Oh wait, 30.07, and this thing's not liking me today. 30.07, and convert it to 763. So right now, there's a little bit of a high pressure system, and that will go back to here. And there are 760 millimeters of mercury in an atmosphere. And here's your initial air volume, so that's before you start the experiment, little bubble, look at that. The final volume, and so the initial minus the final. And then just the reaction time, how long it took. And use a stopwatch. If you forget, you know, just look at a clock and then see how long. It's going to be on the order of 10 minutes. And temperature is degrees Celsius plus 273. You can look this up too. Depending on how hot it is, it might be a little warmer. We'll just see. And then there's the to convert to atmospheres. And the volume, so milliliters divided by 1,000 2 liters. N, so PV equals nRT, so N equals PV over RT. So you have your pressure here, you have your volume here, R is given, and then T. There's your temperature in Kelvin. Be sure to use Kelvin. Oh, and then you calculate it, and then you get the number of moles. So here is your actual number of moles of oxygen using the ideal gas law. And now let's go into here. The molar mass, remember, was up there. It was 34, and 1 over 34. And the theoretical moles of O2. This is assuming 100%. So this is 100%. And if you remember, there's the equation up here, back up here, and we went over it in the exercises. So here, use the amount of H2O2 used, which is around 5 milliliters, and the density, which is 1.02, 1 divided by 34, and times a half. And then that will give you, so coming back down there, using that, you would get, that's this one right here. That's the theoretical moles. That gives you this answer right there. And now, the percentage, you have your actual moles, and actual moles is there, that one, divided by this one will give you the percentage, and I don't think it's going to be 3%. It's going to be a little less, and I don't think it'll be 4%. So no, I'm sorry, my old football coach. We're not going to be given 110% in lab today. I guess 4% would be 133%. He would be very proud of me if I gave 133%. And I would be too. If you guys gave 133%, I would be very proud of you. And this is just the volume of O2 milliliters second. So the volume is this one up here. This is that volume divided by the number of seconds. So if it's 5 minutes, it'll be 300 seconds or 600 seconds for 10 minutes. So that'll give you the milliliter per second. And here was it calculated. So is it 3%? Who knows? And we'll increase the amount of catalyst. Well, you can try this out. There's always a limit. You can just add more yeast and do it again if you want. But catalysts do speed up a chemical reaction. So this one's a little difficult to do, and try your best. There's going to be a little bit of errors going on, not mentioned. There's going to be some leaking here and here, and maybe you throw it in there and it's already reacting before you put the stopper in. So there's going to be a little bit of gas released. You're not going to collect it all perfectly. But do your best and give me a call or drop me a line, send me an email if something happens and you need help, okay? Good luck.